Good day again. In this video, we will start with section 3.2, which introduces the concept of probability distributions of discrete random variables. By the end of this video, you should be able to define a probability distribution of a discrete random variable, of which we will refer to as probability mass function or PMF. You should also be able to verify the conditions that hold for a valid PMF, as well as be able to represent the PMF using a line graph, table, histogram, or a formula. In the next videos, we will have a look at the rest of these points. Alright, so section 3.2 starts off with describing what a probability distribution is. It says when probabilities are assigned to various outcomes in your sample space, then these in turn determine probabilities associated with the values of any particular random variable x. The probability distribution of x says how the total probability of 1 is distributed allocated to the various possible x values. So let us consider an experiment where we have a balanced coin and we toss this coin once and we want to see if we will get a head or a tail. So from this experiment, we have sample space with two possible outcomes. Either you get head or you get tails. Now from these two outcomes, we know what the probability of getting a head is, and we know the probability of getting a tail is, since we assume that it's a balanced coin with only two sides, right? One side head with the other side tail. Now probability of getting a head, it's a half, and probability of getting a tail is also a half. Now suppose that we define a random variable from this experiment. So let random variable x indicate whether you observe or obtain a head or not. So we can let the outcome head be represented by numerical value 1, or the outcome tail be represented by numerical value 0. So for our random variable x, we have possible values 0 and 1. Now using this information here regarding the probability of obtaining a head or tail, can you then use that information to calculate the probability of observing x equal to 0? Or can you use the information then to calculate the probability that x is equal to 1? Alright, so this paragraph here says that the probabilities of the outcomes, the specific outcomes in your sample space, are associated with the probabilities of observing possible values of our random variable x. So since a numerical value of 1 indicates the outcome of head, we know that the probability that x is equal to 1 from this experiment is similar to the probability of observing a head, which is equal to a half. And the probability that x is equal to 0 is the same as the probability of obtaining tails from the experiment, and so that probability is also equal to a half. So we see that for our possible values of random variable x, where x could either take on numerical values 0 or 1, we see that the total probability of 1 is equally distributed amongst the possible values of x. So if you do or draw a table where possible values of x is 0 and 1, and the probability that x is equal to 0 or 1, we see that the probabilities are equally distributed and they add up to a total probability of 1. So we have just described here a probability distribution of a random variable x. This leads me then to the first definition in section 3.2, which says the probability distribution or probability mass function of a discrete random variable is defined for every number x by this notation here, small p, and we have in brackets the possible value for our random variable, And that is equal to probability that x is equal to that particular possible value. Now, this probability of observing that particular possible value x is the same as the probability of observing a specific outcome in your sample space. So in words, for every possible value x of the random variable, the PMF specifies the probability of observing that value when the experiment is performed. So the conditions, the important conditions that hold for a valid PMF is that the probability of observing that specific possible value of your random variable, it must be greater or equal to 0. So probability must be greater or equal to 0. And when you add up all the probabilities, it must add up to 1. So where the summation is over all possible x, and the summation of the probabilities is equal to 1. Alright, so there are 3 ways to represent a probability mass function. The first way is to use a table, or to write it as a formula, or use some graphical illustration such as a line graph or probability histogram. Now you've been hearing the words probability mass function. So for a discrete random variable, so if x is a discrete random variable, then we will call its probability distribution we will refer to it as PMF. P stands for probability, M stands for mass, F stands for function. So the name probability mass function is suggested by a model used in physics for a system of point masses. So in this model, masses are distributed at various locations, x, along a one-dimensional axis. And our PMF describes how the total probability mass function of 1 is distributed at various points along the x-axis, or the axis of possible values of our random variable. So we want to see, just like with our first example, we either had tails or head, and the probability of observing specific possible values of x. In this case, we had a half and half for heads or tails, and the total probability here was 1. So we saw that the probability of observing a value 0, or when x is equal to 0, it's a half. The probability of observing x equal to 1, that is 1, is equal to a half, sorry. And if you add up all the probabilities, a half plus a half will give you a total probability of 1. So the total probability of 1 is equally distributed in this case, only in this case, specific case of tossing a coin, a balanced coin. So we see that the total probability of 1 is equally distributed amongst the possible values of our random variable x. So this whole entire table describes a probability distribution, or this whole entire table is actually the PMF of a random variable x. Let us consider example 3.7, which says 6 lots or containers of components are ready to be shipped by a supplier. The number of defective components in each container is as follows. So we have here, for example, 6 containers labeled 1, 2, 3, 4, 5, and 6. And we have counted the number of defectives in each container. So either have 0 number of defectives, 2 defectives, 0 number of defectives in container 3, 1 defective in container 4, 2 defectives in container 5, and 0 number of defectives in container 6. So one of these containers is to be randomly selected for shipment to a customer. Now let random variable x be the number of defectives in a randomly selected container. Alright, so we have defined our random variable x. Now we want to know what are the possible values of our random variable x, denoted by a small letter x. So we have small letter x equal to, and in brackets we have the possible number of defectives. Right, so we see that you could either have 0 number of defectives, or you could have 1 defective, or you could have 2 defectives in a randomly selected container. Some of them have 0 number of defectives, some have 1, some have 2. Right, so we have here that random variable x can take on values 0, 1, and 2. Now, what is the probability that you would observe x equal to 0, or probability that you observe x equal to 1, or probability that you observe x equal to 2? So we will summarize all this information under what you call a probability distribution, where the total sum of these probabilities must add up to a total probability of 1. Now, how can we represent this PMF or probability distribution? So remember I said if we have a discrete random variable, we will refer to the concept of probability distribution of a discrete random variable as a probability mass function. So probability mass function can be represented either using a table or a formula or some graphical illustration. All right, so using this example, let us have a look and see how can we represent a probability mass function using a table. So we will firstly draw up our table with 2 columns. The first column consists of the possible values of our random variable. Since we have random variable x, I will write there small letter x. Okay, and our second column will be the probabilities of observing these values of random variable x. So it's px, which is the probability that x is equal to that particular random possible value. So in this case, our random variable x can take on values 0, 1, and 2. So I will write here in the first column 0, 1, and 2. Now, what is the probability that you observe the numerical value 0? Or what is the probability that you'd have 0 number of defectives in a randomly selected container? In this case, if we go back to our information, the probability that x is equal to 0, if we count the possibilities of observing 0 number of defectives, we see that we have, out of 6 times, we can observe 0 number of defectives 3 times. So our probability that x equal to 0, that is 3 divided by 6, or that is 0.5. Now the probability that x is equal to 1, what is the probability here of observing only 1 defective in a randomly selected container? We see that 1 appears how many times? Once out of 6 containers. Okay, that is approximately 0.167. And then probability of x is equal to 2, that is the probability of having 2 defectives in a container. We see that out of 6 times, the possibility of observing that is 2. So we have 2 divided by 6, which is then approximately 0.333. That is the probability. Now we will complete this table and represent our PMF using a table. So if x is equal to 0, then the probability that x is equal to 0, that is equal to 0.5, or you can write it as 3 divided by 6. Probability that x is equal to 1, we see here that we have a probability of 1 divided by 6, and probability that x is equal to 2, we have then a probability of 2 divided by 6. Now we need to see, are the probabilities all positive, greater or equal to 0? That's the condition of a valid PMF, that all the probabilities, let me write it properly, small letter p bracket x, they must all be positive, greater or equal to 0. And if we add them all up, it must add up to 1. So we see that the all positive, we have 0.5, 1 divided by 6, 2 divided by 6. So all 3 probabilities are positive, yes. And if we add them up, 3 divided by 6 plus 1 divided by 6 plus 2 divided by 6 will add up to total probability of 1. So we see that the total probability of 1 is distributed in this way for the possible values of a random variable x. So we see that most of the time or it's highly likely that you'd have zero number of defectives, and then you'd see that it is possible to have one defective or two defectives. All right, so now how can we then represent this PMF using a formula? So that was the first way of representing. Now secondly, how do we represent the PMF in a formula way or form? So we will write down P, small letter Px, equal to, remember Px calculates probability that x is equal to that specific possible value. So we'll say Px and then equal sign, and you use this large curly bracket. And so you will write down the formula or the probability for each possible value of x or random variable x. So what is the probability if x is equal to 0? And what is the probability if x is equal to 1? And what is the probability if x is equal to 2? And what is the probability otherwise if x is not equal to 0, not equal to 1, not equal to 2? So we will represent it as a formula in this way, where you write Px equal to, in curly brackets, and you write down the probabilities for each possible outcome. So if x is equal to 0, the probability we see, we calculated it as 3 divided by 6. If x is equal to 1, probability is 1 divided by 6. And if x is equal to 2, probability for that is equal to 2 divided by 6. And let's say x is equal to 10. Is it possible in this scenario to have 10 number of defectives? No, it's not part of the data. It seems to be impossible in this scenario or context. So the probability for any other x that is not 0, 1, or 2 will be probability of 0. So this is how you would write it as a formula. Good. Now how do we represent the PMF using line graph or probability histogram? So graphically, we know that if you draw any graph, you have to start with a title, right? So you can write down your title, line graph, illustrating PMF of random variable x, where random variable x denotes the number of defectives in a randomly selected container, right? And then you will draw your axes. In this case, your y-axis, you will write down your probability values, and on the x-axis, you will write down your possible values of a random variable. Since our random variable is denoted by capital letter X, it makes sense for me to write down small letter x on the x-axis. But if my random variable was capital letter Y, then I will write down on my y-axis py, and on the x-axis I will have small letter y, because these are the possible values of my random variable y. So it depends on your random variable, okay? So either you have py there, if you have random variable w, you have pw, and you have w there on the x-axis as possible values. In this case, we will have a look at random variable x, and so that's why I have x on my x-axis there, and I have px labeled there on my y-axis. Now we know that everything, or your graph will start at the origin or 0, not everything. Your graph will start at the origin or 0, and you have possible values 0, 1, and 2. Now for a line graph, you will draw lines for probabilities that corresponds to your possible values of random variable x. So we see that if you observe x equal to 0, then the probability for that is a half. So we have there 0.5. So we will draw a line up until corresponding y value there, 0.5 for x equal to 0. For x equal to 1, the probability is 1 divided by 6. So you draw a line up until that corresponding point there. And when x equal to 2, we see the probability is 2 divided by 6. So you draw a line up until the corresponding point there. So that's a line graph. Then a probability histogram. If you draw a graph, you know that you start with the title, you give it a nice title that makes sense. So probability histogram, or my title could be probability histogram, stating PMF of random variable x. And you can make a note what random variable x is anywhere, say below the table or as extra information. So it doesn't have to be part of the title. Okay, then you draw your axes. Again, on the y-axis, I have px because I have calculating probability or indicating a probability of observing certain values for random variable x. And so on the x-axis, I'll have small letter x because I'm working with random variable x in this scenario. Okay, and we have possible values 0, 1, and 2. Okay, so now for a probability histogram, instead of drawing lines, we will be drawing bars or columns. Okay, so we have here 0.5, 1 divided by 6, 2 divided by 6 there. And so your probability histogram will look as follows. So you'd have a column. For x equal to 0, your column will look like that. So you have 0 in the middle there. For x equal to 1, we have probability of 1 divided by 6. So you have column like that or a bar like that. And so for x equal to 2, since probability is 2 divided by 6, we will have then the bar that goes up to probability of 2 divided by 6. And that is how you can represent a probability mass function. So I can ask you in a test or anywhere to define or represent it either using a table or as a formula, or in terms of graphical illustration as a line graph or probability histogram. All right, good.